Okay, so hopefully you've watched that video, the Mythbusters, where they shot the bullet and they fired. So they fired one and they dropped one, and their question was, which one hits the ground first? And I hope that you were able to see that even though there was a slight difference in the amount of time it took for those two bullets to hit, that difference can be explained by two things. Number one, they didn't take into account air resistance, which affects the fired bullet a whole lot more than the one that was dropped. And you can tell that if you drive down the road and stick your hand out the window of the car. You can definitely feel the air resistance on your hand, whereas if you're just walking down the sidewalk and do the same thing, you don't feel that quite as much. So air resistance affects those two bullets differently, and if we can get rid of the air, then those two bullets will drop at the same time. Another thing that they did is they wired a mechanism at the end of the airplane hangar to drop the bullet at the same time that the bullet was fired from this end. And it took some time for that signal to propagate from one end to the other. Those two things, the time it took for the signal to propagate and air resistance, account for the very, very slight difference in the amount of time it took for those two bullets to hit the ground. But for all practical purposes, and if we can get rid of those two variables, then those two bullets hit the ground at the same time. And so I ask you, what does that mean? What does it mean that the bullet that was fired hits the ground at the same time that the bullet that was dropped? And I want you to see what kind of misconception that you might have in your head at this moment about that. Because if you're like me, I thought that the bullet that was dropped would hit the ground first. And there are two reasons for that generally. Number one, you tend to think that the bullet that is dropped has a shorter distance to travel, therefore it should hit the ground first, right? After all, this bullet is traveling a very long distance for the bullet. It does something like this, and the bullet that was dropped simply does like this. This is a much, much smaller distance. You think this one's covering a longer distance, so it's going to take longer to actually get to the point where it's going to hit the ground. Another reason is that in your mind, you think that giving something horizontal velocity is going to keep it in the air longer. In other words, your mind wants to tell you that giving something horizontal velocity can somehow counteract the force of gravity, which is constantly pulling downward on this projectile. For instance, if you kick a soccer ball off a building and that soccer ball falls like this, and if I tell you, what can you do to keep the ball in the air longer? You might say, well, kick the ball harder. And you would do like this, kick the ball harder. And you think kicking the ball harder, giving it more horizontal velocity, might keep the ball or the bullet in the air longer. But if those two bullets fall at the same time, what did that prove to us? Well, it proves that it doesn't matter what kind of horizontal velocity we give to a projectile. That bullet was shot out at close to 600 meters a second or something like that. It was an amazing horizontal velocity. We gave it about as much horizontal velocity as we can, as is humanly possible. And we dropped another bullet from this end at the same time. And the question is, did this amazing horizontal velocity actually affect, or did it actually change the effect of gravity on the projectile? And the answer is no. Because both objects took the same amount of time to hit the ground. In other words, if this one took 0.3 seconds to hit the ground, this one took 0.3 seconds as well. This is a projectile. The definition of a projectile is something that's moving through the air under only the influence of gravity, and it has an x dimension to its motion, and it has a y dimension to its motion. In other words, this projectile is moving forward, definitely, but it's also falling downward at the same time, and those two parts of the motion operate independently. And that is the point of the bullet versus fired video. And you can think about it this way. Whenever you watch cartoons as a kid, you used to watch those Wile E. Coyote cartoons, right? And if you didn't ever watch them, there's a link on the bottom of the video right now. You can go watch a video that shows you what I'm about to show you. But in those cartoons, here's what Wile E. Coyote frequently does. He walks to a cliff, or he runs to a cliff, runs, and then he'll usually run or walk off the edge of the cliff, and he's literally walking on air, right? They do this in cartoons all the time. And then as soon as Wile E. Coyote realizes that, oh crap, I'm not on the edge of the cliff anymore, it's then that he falls straight down. Now you and I know that that doesn't happen in real life. It doesn't happen in real life. And if you were in class, I showed you that video and I said, this illustrates projectile motion. You might have been confused by that. And here's the reason why I wanted to illustrate projectile motion. The x component of a projectile's motion and the y component of a projectile's motion are completely independent and separate from each other. They don't affect each other. And we illustrated that with the bullet. We gave the bullet as much horizontal velocity as we possibly could. And if giving something horizontal velocity could cause it to change its y motion, then that would have happened. But we saw that giving it horizontal velocity didn't affect the y motion at all, because this one fell the same amount of time that this one did. The y motion was exactly the same in these two, even though the x motion was completely different. And that's how I want you to think about projectile motion. Think about Wile E. Coyote. First he goes out in the x direction, and then he goes down in the y direction. Instead of what actually happens in real life if you run off a cliff, it would be something like this. The way that we have to analyze all these problems in physics is in terms of stuff in the x direction, horizontal, and in stuff in the y direction, vertical. It's kind of like when we talked about vectors, and if we have a vector, say we have a projectile that's moving at 90 meters per second at an angle that's 45 degrees above the horizontal. What we first have to do to this vector is we have to resolve it into the x and the y components. The reason being because this vector that we're given is neither in the x or y direction. It's kind of like when you used to use an Etch-a-Sketch when you were a little kid. Remember, you turn the dials. This one over here draws a left and right line, and this one over here draws it up and down. So if I just turn this one, I can make a perfectly straight line left or right. And if I turn this one, I can make a perfectly straight line up and down. Well, how do you make a slanted line? Well, you do a combination of the two. You kind of dial in this one, you turn this one, and you turn this one at the same time, and you end up getting a probably crooked line, because if you could draw a straight slanted line with an Etch-a-Sketch, you were pretty good. I never could do that. But the point is that both the horizontal and the vertical add together to produce what we get here. And it's the same with projectile motion. We have some horizontal motion going on at the same time we have some vertical motion going on. They happen to be going on at the same time in the same object, but they do not affect each other. They are completely independent. The big major league point that you must remember with all projectile motion is that the x motion, the motion in the horizontal direction, is completely separate and independent from the motion in the y direction. We analyze both at the same time, but the motion in one direction does not affect the motion in the other direction. So let's consider what would happen as you run off a cliff, right? So let's redraw what happens here. Let's say that you're running off a cliff. Let's make it a little more exaggerated here. You ran off a cliff really fast, and there's your trajectory. And at each point along this trajectory, I can draw a vector that represents the direction of my actual speed at that moment. So this vector up top might look like this, and then it might look like this here, and at the bottom it would be this. The question is, at each point, that vector, since it's not in an x or y direction, it has to be resolved into x and y components. So let's do that. If I did that, all I have to do is complete the triangle. There's my x, there's my x, and there's my x. Y component would be here. Y component, y component. So the question is, what happens to the x and the y components as the projectile moves to the ground? Let's take the x first. No, let's take the y first. What happens to the y components of the velocity as that projectile moves to the ground? Well, you might be able to tell by the length of these vectors, they get longer and longer and longer. What that means is that the y component of the speed of this projectile increases as it moves to the ground. In other words, in the y direction, speed increases. Why? Well, the reason why speed increases, we might want to answer that question, I'll ask another question. How do you get the speed to increase in your car? Well, you hit the gas. In other words, you apply a force. How do you get your car to stop? You hit the brakes. You apply a force. In other words, and we'll learn about this when we get to forces, in order to change the speed of something, you must apply a force. and there's a force that's being applied in the vertical direction, that force is called gravity. If gravity is being applied, speed has to be increasing. In other words, in the y direction, all this is a free fall problem. And we've done free fall problems before. In the y direction, speed increases because it's a free fall. It's subjected to gravity. What about the x direction? If you look at these vectors in the x direction, and I drew these purposefully this way, you might be able to tell that the length of those vectors is the same approximately, as far as my drawing is concerned, all the way to the ground. Which means, does the x direction speed change as the velocity, as the projectile gets to the ground? And the answer is no, it doesn't. For the same reason why the y speed does. The y speed changes because there's a force being applied in the y direction. In this class, we get to neglect air resistance. If there was air resistance, this projectile would slow down in the x direction because air resistance is pushing against it. But if there's no air resistance, and in this class we can neglect air resistance, not if you're doing pre-AP or AP or college level physics. But if we neglect air resistance, the question is, once we leave the cliff, is there any force acting in the horizontal direction? No, there's not. There's no force acting. Which means if there's no forces, that means there's no change in speed. Which means in the x direction, this speed is always constant. The x speed is constant, the x direction is constant velocity, the y direction is increasing velocity because of gravity. So there you are, basic horizontal projectile motion. The big major league point that you must remember is that the motion in the x direction is completely independent of motion in the y direction. They happen at the same time, in the same object, but they do not affect each other.